Now let's go over the first derivative test. This is a test used to locate and identify relative extrema for a function. So to see how the test works, consider the two graphs that we have down here. Notice for the first graph, we have a relative minimum when x is equal to c, and for the second one we have a relative maximum when x is equal to c. Now, for the one that has the relative minimum, notice that to the left of c, our function is decreasing, so that means that our derivative will be negative to the left of c. Then to the right of c, our function is increasing, so that means that our derivative will be positive. For the other one that has the relative maximum, notice that to the left of c, our function is increasing, so that means our derivative will be positive. And to the right of c, our function is decreasing, so that means that our derivative will be negative. So we can use this to create a test to identify relative extrema. So if we have a point where our derivative is 0 or does not exist, and we see that to the left of that number our derivative is negative and to the right it is positive, then we know that we're going to have a relative minimum. Or if we see that to the left of that number our derivative is positive and to the right it is negative, then we know that we're going to have a relative maximum at that point. And that's our first derivative test. Here we have a precise statement of the first derivative test. We need to place some conditions on the function f of x. So we start by assuming that c is a critical number for a function f of x, and that the function is continuous at c and differentiable in an open interval about c, except possibly at c itself. The function doesn't have to be differentiable at c. It might have a cusp at c, but our first derivative will still work in that case. Then we have these three cases. Case 1, if the derivative changes sign from negative to positive at c, then f of x has a relative minimum at c f of c. So remember, if the derivative goes from negative to positive across c, that means that your function is decreasing and then increasing, and so at c f of c you're going to have a relative minimum. Case 2, if the derivative changes from positive to negative at c, then f of x has a relative maximum at c f of c. So if your derivative is positive and then negative, that means that your function is increasing and then decreasing, so you're going to have a relative maximum at c f of c. Our final case, if the derivative does not change sign at c, then f of x has neither a relative minimum nor a relative maximum at c f of c. To understand the third case a little bit better, let's look at these two graphs down here. So notice for this first graph, our derivative is 0 at c, so we do have a critical number, so c is a critical number. The derivative is 0 right here because we have a horizontal tangent line. And notice that we do not have a relative minimum nor a relative maximum at this point. Notice also to the left of c our function is increasing, so our derivative is positive to the left of c, and to the right of c our function is still increasing, so our derivative is positive here as well. So notice that as we move across c from the left side to the right side, our derivative does not change sign. So that's what case 3 is talking about. On the other hand, we could have something like this. This is similar. Notice right here c is a critical number because our derivative is equal to 0 at c, right there. And notice to the left of c, our function is decreasing, so that means that our derivative is negative. And to the right of c, it continues to decrease. So our derivative is still negative. So at this point, our derivative is 0, but we don't have a relative minimum nor a relative maximum. And notice that our derivative does not change sign. It stays negative to the left, and then it remains negative to the right of c. So that's another example of case 3. Now let's take a look at a few examples. For this example, we want to find where the function 2x cubed plus 6x squared minus 48x is increasing or decreasing, and identify any relative extrema. So to find where the function is increasing or decreasing, we first of all have to find all of our critical numbers for this function. So we want to find where the derivative is 0 or does not exist. So our derivative is and we want to find where that is 0 or does not exist. Now, for this example, we're not going to have to worry about not existing because this is a polynomial, which of course exists everywhere. If it were a rational function, we would have to worry about where the denominator is equal to 0. That's where our derivative would not exist. So we just need to set this equal to 0 and solve for x. Now, this does factor as and that further factors as and now setting each individual term equal to 0, we get that x is equal to -4 or 2. And these are our critical numbers. So now we're going to use the sign pattern technique to determine where our function is increasing or decreasing. So we're going to set it up like this. So we set up our number line, we put our critical numbers on it, -4 and 2, and this is going to represent the sign of our derivative. And then we just have to pick some test values in each interval. For example, -5 we could choose to the left of -4, 0, and 3. And now what we're going to do is we're going to put these numbers into our derivative and see which are positive and which are negative. Now we're going to put them into the factored form right here. Oftentimes when you're doing these problems, you'll have a factored form. It's a little easier to put the numbers into there and determine whether they're positive or negative. So if we put -5 in for x here and here, we're going to get a positive number, 6 is positive, times a negative number, -5 plus 4 is negative, and times -5 minus 2, that's negative. So a positive and 2 negatives, that makes a positive. So our derivative is positive from -infinity to -4. If we put 0 into our derivative, we're going to get back positive times negative. And that will be negative. So our derivative is negative from -4 to 2. And if we put 3 in for x here and here, we're going to get a positive number times a positive times a positive. 3 minus 2 is positive. So our derivative will be positive from 2 to infinity. So now we can identify where our function is increasing and decreasing. So we see that our function is increasing on the intervals from negative infinity to negative 4, and on the interval from 2 to infinity. That's where our derivative is positive. And our function is decreasing on the interval from negative 4 to 2, because that's where our derivative is negative. Now we can identify relative extrema. Notice that at negative 4, our function is increasing and then decreasing. And so at negative 4, we're going to have a relative maximum. So we have a relative max when x equals negative 4, or we could put it as the point negative 4, f of negative 4. Note we have to put the negative 4 back into the original function to get the point on the graph that is the relative maximum. And if you put negative 4 into this function up here, you're going to get back 160. So here's the point that represents the relative maximum. So that's the point on the graph that is the relative maximum. And the relative minimum, that's occurring when x equals 2, or the point on the graph that is the relative minimum would be 2 f of 2. And if you put 2 into the original function, you will get back negative 56. Just check that out on your calculator, put those numbers in here for x, and you'll get back 160 and negative 56. And there we go. We have found where our function is increasing, decreasing, and we've identified relative extrema. Let's take a look at the graph of this function now to see that everything that we've done here matches up with the graph. So here's the graph of that function. Notice that we have a relative maximum right there. That's the point negative 4, 160. And we have a relative minimum right here at 2, negative 56. And notice our function is increasing from negative infinity to negative 4. This is where we're increasing. Decreasing from negative 4 to positive 2. So that's where we're decreasing. And then increasing again from 2 to infinity. And so everything here matches with what we found analytically. Let's take a look at another example. So here we want to find where the function f of x equals x squared minus 9 to the 2/3 power is increasing or decreasing, and locate all relative extrema. So if you want to, you could pause the video here and try this one on your own. So I'm going to go over it now. First thing we want to do, find our critical numbers. So we want to take the derivative. Derivative of this function is going to be okay, there's our derivative, and let's clean that up a little bit. Let's write that as we'll write it like that. Now we have to find where this is 0 or does not exist. Alright, so it's going to equal 0 when the numerator is equal to 0. So if we set 4x equal to 0, we get back that x equals 0. That is one of our critical numbers. On the other hand, if we set the denominator equal to 0, that's where our derivative is not going to exist. So if we set well, this will equal 0 when this implies that x squared minus 9 is equal to 0, and that implies that x is either plus or minus 3. So there are two more critical numbers. Those numbers are where the derivative does not exist. Notice, plus or minus 3 satisfy this equation. X squared minus 9 equals 0. This also factors as x plus 3 and x minus 3. Now we can find where our function is increasing and decreasing by putting these on a number line and using a sign pattern technique. And then we just have to pick some convenient numbers in between, like, let's say, -4, -1, +1, and 4. And then we just have to put each of these into our derivative. We're going to put them in here and see if we get back positive or negative numbers. So remember, this number line is representing the sign of f prime. So if we put -4 up here in for x, well, the numerator will be negative, right? 4 times -4, that will be negative. And the denominator, well, let's see, -4 squared is going to be 16 minus 9. That will be a positive number. So we'll have negative over positive. That will be a negative number. So our derivative is negative from -infinity to -3. If we put -1 in for x, the numerator will be negative. The denominator will also be negative because we'll have -1 squared, that's 1 minus 9. 1 minus 9 is 8 to the 1/3 power. That is, -8 to the 1/3 power. That is negative, right? Once again, when we put -1 in here for x, we get +1 minus 9, that's -8 to the 1/3 power, and that is negative. Okay, so we get negative over negative. That is positive. If we put 1 in for x up here, we will get a positive numerator divided by a negative number. Once again, 1 going in for the x will give us back -8 to the 1/3. That is -2, and so that is negative. So we're negative in this interval, and then if we put 4 in for x up here, we'll have a positive number divided by a positive number. 4 squared is 16 minus 9. That's going to be positive, and so positive like that. There we go. Now we can determine where our function is increasing and decreasing. So we see from the number line here that our function is increasing from -3 to 0 and from 3 to infinity. Our function is decreasing from -infinity to -3 and from 0 to 3. Now let's identify relative extrema. So we see that we have a relative maximum Let's see, relative maximum, that's going to be at 0, right? Because our function is increasing and then decreasing right at 0. So 0. And if we put 0 in, now have to be careful, we put 0 into the original function up here. So 0 f of 0, that will be negative 9 to the 2/3 power. Now if you evaluate negative 9 to the 2/3, because you're squaring it, this will become positive down here. Evaluate that on your calculator. 4.33. That's what you get if you evaluate this on your calculator. Be careful when you evaluate this on your calculator. It should be entered as parenthesis negative 9 hat, and then be careful with your parentheses, 2 divided by 3, like that. That's how you would enter this into your calculator. You'll get back 4.33. Then we have another relative, no, we don't have any other relative maximum, sorry. We have relative minimum. Let's see, our function at negative 3, our function is decreasing and then increasing. So right here is going to be a relative minimum. So that's going to be at negative 3. And if we put negative 3 in for the x up here, we're going to get back 9 minus 9. That's just 0. And at 3, we have another relative minimum. Notice our function is decreasing and then increasing. So at 3, and f of 3 is also going to be 0. So here we have our relative minima. So there we've identified everything. We found where our function is increasing, decreasing, and we've identified relative extrema. Let's take a look at the graph of this function and see if everything matches up with the graph. So here's our graph. Notice that we have relative minima at, that is negative 3, 0. And right here is 3, 0, just like we've found. Right here we have a relative max that is at 0, 4.33. And notice our function is decreasing from negative infinity to negative 3. Then from negative 3 to 0, we are increasing. Then from 0 to positive 3, we are decreasing again. And then from 3 to infinity, we are increasing. And so that matches up with what we found. Let's take a look at one more example. So let's find where this function, x plus 1 over x squared, is increasing or decreasing, and we'll locate all relative extrema. So we want to find where this function is, where the derivative is 0 or does not exist. Now our derivative is, there's our derivative. Remember, you should write 1 over x squared as x to the negative 2, and when you differentiate, you'll get negative 2x to the negative 3. Now we want to set this equal to 0, and also find where it does not exist. So first of all, setting this equal to 0, let's see. Well, we can sort of just look at this and see it's going to be where x cubed is equal to 2, right? So x is going to be the cube root of 2. If you didn't see that right away, just take this over to the other side. You get, multiply the x over, and then just take the cube root of both sides. And there is one critical number. That was where the function, where the derivative was equal to 0. Now we need to find where the derivative does not exist. Well, just looking at this, we can see that the derivative does not exist when the denominator here is equal to 0. So when x cubed is equal to 0, that implies that x equals 0. That's where our derivative does not exist. So that's another critical number. So we need to plot these two numbers on the number line and use our sign pattern technique. 0, and we'll put the cube root of 2 right here. Now notice the cube root of 2 is approximately 1.26, so that way we can pick numbers on either side of it. We need to identify what its decimal expansion is. So now we'll pick some test numbers like -1 and 1 and let's say 2. So we'll pick these numbers, put these numbers into the derivative, and see what the sign of f prime is. So if we put -1 into the derivative here, we're going to get 1 minus 2 divided by -1, right? If you look at 1 minus 2 over -1 cubed, that's going to be 1 plus 2, right? Because -1 cubed is negative, so you're going to have minus a negative number. So this is positive, so our derivative is positive in here. Now if we put 1 in here for x, we're going to get 1 minus 2. So that will be negative. And if we put 2 into our derivative up here, we're going to get 1 minus 2 divided by 8. So that's 1 minus 1/4. And of course that's positive. So, and there we go. So there's where our derivative is positive and negative. That tells us where our function is increasing and decreasing. So our function is going to be increasing from -infinity to 0, and from the cube root of 2 to infinity. So those are the two intervals over which our function is increasing, and then our function is decreasing from 0 to the cube root of 2, because that's where the derivative is negative. Now let's identify relative extrema. So let's see, at 0, our function is increasing and then decreasing. So it looks like 0 might be a relative maximum, because our function is increasing and decreasing. However, if we go back to the original function and try to put 0 in here, we see that we can't, because we get 1 divided by 0. So that's actually where our function has a vertical asymptote right here. So that's actually not a relative extrema, because our function does not exist at 0. So we can't list this as a relative maximum. Now at the cube root of 2, our function is decreasing and then increasing. It looks like this is going to be a relative minimum. Just double check, can we put the cube root of 2 back into our function? Yes, we have no problem there. So we only have a relative minimum at the cube root of 2, comma, and if you evaluate the cube root of 2, if you put the cube root of 2 in for x into the function up here, you will 1.89 approximately. And that's where we're going to have a relative minimum. So there we found where a function is increasing, decreasing, and we identified all relative extrema. Once again, notice that when x is equal to 0, this function does not have a relative extrema at that point, because it actually has a vertical asymptote. Because if we try to put 0 in for x, we get that f of 0 is of the form 1 divided by 0, that indicates we're going to have a vertical asymptote at x equaling 0. Now let's take a look at the graph of this function, see if everything matches up. So here's the graph. Notice that we have a relative minimum right here. That number right there is the cube root of 2, approximately 1.26, and the y-coordinate was 1.88, so that looks good. Notice our function is increasing from negative infinity up to 0, which is what we found. It is then decreasing from 0 to the cube root of 2. So here it's decreasing. Notice it's coming down from infinity. And we're increasing again from the cube root of 2 to positive infinity. Also notice that at x equaling 0, we do have this vertical asymptote. So everything seems to match up with what we found. And that concludes our discussion of increasing and decreasing functions and the first derivative test.